Good evening. You may remember that last month I said that when the planet Venus passed close to the star cluster of the Hyades, it would make rather a nice picture. Well, I'm afraid that on this occasion, sultry weather let me down, and I was completely clouded out. But over in Hampshire, Douglas Arnold wasn't. He's a far better photographer than I am anyway, and he took this picture. And over to the left, you can see the crescent moon, and you'll also notice that the so-called night side of the moon is shining faintly. And there's no mystery about that. It is due to light reflected onto the moon from the Earth, and we call it the Earthshine. And you'll nearly always see that when the moon is a crescent. In the middle of the picture, there is Venus. Now, a really spectacular object in the eastern sky before dawn, much brighter than any other star or planet. And extending away from Venus to the right-hand side, you can see the little V arrangement of stars that marks the Hyades cluster. And that brighter star lower down, just above the cloud, is Aldebaran, the orange-red eye of the bull. In point of fact, Aldebaran is not really a member of the Hyades at all. It simply happens to lie more or less halfway between the Hyades and ourselves. And the Hyades make up what we call a moving cluster. And I'm going to have more to say about moving clusters in a few moments. Obviously, the solar system has been very much in the news lately. And incidentally, the Giotto probe to Halley's Comet appears to be going well. But this evening, I want to leave the solar system, go far outside it, and talk about the stars, or one particular star, Mizar, in the constellation of Ursa Major, the Great Bear. And I think everyone's heard of the Great Bear, and that's a picture of it from a lovely old set of cards called Urania's Mirror. I've always thought that to make the outline of a bear from the main stars in Ursa Major takes quite an effort of the imagination. But it's a lovely old picture, and there is also a legend about it. According to this legend, Ursa Major used to be a beautiful princess named Callisto. And Callisto was so lovely that her beauty was greater than that of Juno, the queen of the gods. And Juno was notoriously jealous. So, ill-naturedly, she turned Callisto into a bear. Years later, Arcas, Callisto's son, was out hunting when he encountered the bear, and not realizing it was his mother, was just getting ready to shoot it when Jupiter, the king of the gods, intervened. He turned Arcas into a bear also, caught both animals by their tails, and swung them up into the sky, which is where we now see them. And that's why both the bears have got rather long tails. Now, the 7 main stars of the Great Bear make up the pattern that I think everyone knows as the Plough, or in America, as the Dipper. They are not outstandingly bright, but they do make up a very distinctive pattern, and I think you can't mistake them, particularly as over Britain they never set. They've all got names. In order, they are Alcade, Mizar, and that's the star I'm talking about later, Alioth, Megrez, that's the faint one, Fad or Fector, and Merak and Dupé. Dupé is decidedly orange, by the way. And Dupé and Merak are known as the pointers because they show the way to the pole star Polaris, which lies within 1 degree of the polar point and which therefore appears to remain practically stationary. All you have to do is to take a line from Merak through Dupé, and you'll come straight to the pole star. And then, when the sky is fairly dark, not, I think, during moonlight, you'll be able to trace the outline of the little bear curving down over the Great Bear's tail. And there's one other brightish star in it. That is Kochab, just about the same brilliancy as the pole star, but decidedly orange instead of white, which shows that its surface is at a lower surface temperature. Now, of the Plough stars themselves, 6 of them are very much the same brilliancy. It's the 7th one, Megrez, which is decidedly fainter, and you can notice that straight away. There is a minor mystery there, because apparently the old astronomers of 2,000 years ago didn't reckon Megrez as being very much fainter than the others. But I don't think there's been any real change, because Megrez isn't that kind of star. It's a hot white star, and I think we're much more probably dealing with some kind of mistake in either interpretation or translation. Now, a little while ago, when talking about the Hyades, I mentioned moving clusters. And a moving cluster is made up of stars which are going through space in parallel paths at about the same rate, and presumably have a common origin. It so happens that of the 7 stars in the Plough, 5 of them make up a moving cluster, and 2 of them, Alcade and Dupé, do not. Now, the stars are not genuinely fixed in space. They're moving about in all sorts of directions at all sorts of rates, but they're so far away from us that their individual or proper motions are extremely slight. And so far as naked eye observers are concerned, the constellations look the same over a great many lifetimes. But over a long enough period, then the proper motions do show up. And the Plough has not always looked the same as it does now, and neither will it in the future. And it's rather interesting to go back and forward in time and just see what has happened and will happen to the Plough. So there we have it, 50,000 years ago. It's come forward, 25,000, and there's the pattern as it is today, the familiar Plough. But now watch Alkaid to the left and Dupe, the upper pointer. And you will see from that that they're going in a direction opposite to those of the other 5 stars. And so as we go forward, a long way, 25,000 years, 50,000, 75, 100, 25, 150, 175, and now 200,000 years in the future, you will see that the Plough no longer has its characteristic shape because of the relative motions of Alkaid and Dupe. And in 200,000 years from now, the Plough will look like that. But let's come now on to Mizar itself, much the most interesting of the Plough stars, I think. As I've said, it has a faint star, Alcor, close beside it. And you can see that easily with the naked eye. You know, the estimates of star distances are not always entirely consistent. And in one recent catalogue, Alcor is made considerably further away from us than Mizar. But I think it's much more likely that they are close together in space, comparatively speaking, and probably not more than a light year or so apart. They are certainly about 88 light years away from us, so that when we look at them now, we are seeing them as they used to be 88 years ago. And there's a picture of Mizar and Alcor. But when you look at them through a telescope, you'll see something else. We have Mizar, we have Alcor, and there is also a third star, and you can see them there. Mizar to the lower right, Alcor to the upper left, and the third star over lower down to the left-hand side. And that's very often known as Ludwig's star, because there was a lovely old story. It appeared round about the year 1723 in honor of the Emperor Ludwig V. Well, I can assure you that it didn't. It's certainly not that kind of star, and neither is it connected with the Mizar system. It's in the background. But there is a minor mystery here, because the old Arabs of 1,000 years ago said that Alcor was a test for naked eye visibility, and of course they had no telescopes. Well, that certainly is not the case today. Anyone with normal eyesight can see Alcor without the slightest difficulty when the sky is even reasonably dark. I can do so with no trouble at all. And the Arabs were keen-sighted people, and I've no doubt that 1,000 years ago, the skies were a great deal less polluted by light and dust than they are today. So what's the answer to that one? Why should the Arabs say that Alcor was a difficult naked eye test when today it's not? One suggestion, which I don't personally believe, is that the cause is Ludwig's star, which has been regarded as a variable. Let's have a look again at the configuration. Mizar, Alcor, Ludwig star. Now just suppose that Ludwig star brightened up. If it did that and became as bright as Alcor, then I suppose it might come within the range of naked eye visibility. And now it's faded down again. And at the present moment, it's way, way beyond naked eye visibility, and you can't even see it with binoculars. Personally, I don't believe that, because it doesn't seem plausible to me. I don't believe that Ludwig's star is variable to that extent, and even if it did brighten up, it would still be very inconveniently close to Mizar. So once again, I think we're dealing with some kind of mistake in interpretation or translation. All the same, it is very strange. Now, when you look at Mizar through a telescope, you will see something else. Mizar itself is made up of 2 stars so close together that to the naked eye, they appear as one. Their apparent separation is 14.5 seconds of arc, and that's not a great deal too close for them to be separated with binoculars. One star is rather brighter than the other. Their actual magnitudes are 2.3 and 3.9. And that's the kind of telescopic view you have. 2 Mizars, 1 Alcor, and of course Ludwig star. Now we know today that double stars are very common in space. That wasn't known a long time ago. And in fact, Mizar was the first telescopic double ever to be recorded. And that was done in the year 1650 by an Italian astronomer named Riccioli. Now Riccioli was a good observer. I think we remember him best these days because he drew up a rather good map of the moon and actually gave names to the lunar craters, most of which we still use. But he also observed stars, and when he looked at Mizar, he saw, even with his low-powered telescope, that Mizar was double. Of course, by any modern standards, it's extremely easy, and any small telescope, I think, will show the 2 Mizars perfectly clearly. but it wasn't known way back in the 17th century, and so Mizar did produce something of a surprise. Now today, many, many thousands of double stars are known. In some cases, the components are equal. In some, they are rather unequal, as with Mizar. And in some cases, a bright star is accompanied by a very faint companion. Sirius the dog stars like that. But we also know that double stars are of two entirely different kinds. Optical doubles, which are line-of-sight effects and not genuinely made up of associated components, and binary stars, which really do make up connected systems. Let me show you what I mean. Here we have a studio representation of a double star. The real star appears as points of light, and in the studio we've had to use globes, but the principle is exactly the same. And it looks as if those two stars are very close together. But in point of fact, they aren't. One is very much closer to us than the other. As you can see, this star is in the foreground and is not related in any way to the star in the background. It's merely a line of sight effect. And that's what we call an optical double. And some double stars are like that. But rather surprisingly, most double stars are not optical pairs at all. They are genuinely associated or binary systems. Here again, we have the same kind of thing as before, and it looks just the same as the optical double did. But this time, the two components are genuinely associated with each other, and they are moving round their common center of gravity, in a period that may be very short, if the two are close together, or thousands or even millions of years if the pair is very widely separated. And that's the case with Mizar. It makes up a binary system, but the two components, the brighter one, Mizar A, and the fainter one, Mizar B, are a very long way apart, something like 35,000 million miles. And there we see them, and let's put in the solar system to the same scale, that kind of bullseye thing in the middle, and the outer circle represents the orbit of Neptune, the outermost planet. And as you can see, it could fit quite a number of solar systems in between Mizar A and Mizar B. But all the same, the two Mizars really are genuinely associated, and they make up a binary system, even though the revolution period must be a great many million years. But that's only the start. Mizar A, that's the brighter component, is about 70 times as luminous as our sun. But in 1889, the American astronomer Edward Pickering made a remarkable discovery. Mizar A is not a single star. It's a very close binary. But as the components are only about 18 million miles apart, you can't see them separately. They just appear as a single point of light. And so, how could this discovery be made? And the answer is by using the spectroscope. Now, just as a telescope collects light, so a spectroscope splits it up. And when you use a spectroscope together with a powerful telescope and look at the light of a star, you will see that it's spread out into a colored rainbow from red at the long wave end of the spectrum through the colors of the rainbow to blue and violet at the short wave end. And that colored band is crossed by dark lines. And every one of those dark lines is the particular trademark of some special element or group of elements. And so by identifying those dark lines, we can find out what materials make up the star. There's a rather amusing story there. Way back in the last century, the French philosopher Comte made the statement that one thing that mankind could never possibly find out would be anything concerning the chemistry of the stars. And by now, we know a great deal about it, which only goes to show that when a French philosopher makes a profound statement, he's almost certain to be wrong. But that may tell us about the makeup of the stars, but how can it show that some stars are very close binaries? And the answer is by using what we call the Doppler effect. Now, light is a wave motion, and the color of the light depends on its wavelength. The longer the wavelength, the redder the light. Now, consider an object which is going away from the observer. Here we have a representation of that. Underneath we have two spectra. The bottom one is a standard spectrum, and the upper one is the spectrum of a star. And as the star moves away from the Earth, fewer light waves per second enter the eye than would be the case if the star was staying still. Therefore, the wavelength is effectively lengthened, and the star appears slightly too red. Now, the actual color change is very slight indeed, but the effect shows up in the shifts of those dark lines. And if the dark lines are shifted over to the red end of the spectrum, as they are in the upper band here, then that indicates that the star is going away from us. Now consider a star which is coming towards us. This time, the waves are bunched up. More light waves per second enter the eye than would otherwise be the case. Therefore, the object appears slightly too blue, and all the lines are shifted over to the short wave or blue end of the spectrum. That is the Doppler effect, and by measuring the shifts of the lines, we can tell whether the star is coming towards us or going away from us. Now let's consider the situation with a star that's really made up of two, going round each other in a fairly short period, in the case of Mizar A, about 20.5 days. Now, when the stars are moving in a transverse direction, they are neither going towards us or coming away from us, and that means that there are no Doppler shifts. And that's the situation here. Once again, we have a comparison spectrum at the bottom, the star spectrum on the upper part of the band, and there we have the two components of Mizar. And there, since the motion is transverse, the lines appear single. But when the stars move round their common center of gravity, one star is always going away from us and shows a red shift, and the other star is coming towards us and shows a blue shift. And so the lines are shifted to either side of the mean position. When the motion is transverse, the lines are superimposed, but most of the time, the lines are doubled. And by finding out that the lines appeared single every 20.5 days, Pickering was able to show that Mizar A really is a binary system. And that was the first known spectroscopic binary. Well, now there are plenty of others. Many, many thousands of spectroscopic binaries have been found since then. But this was the discovery that paved the way to all the rest. So the system of Mizar seemed to be becoming more and more interesting. But then it was found that Mizar B, that's the fainter component, is also a spectroscopic binary, this time with a period of 182 days. There may well be a third component in the Mizar system with a period of over 1,000 days. And just to make things even more complicated, Alcor itself turns out to be a very close spectroscopic binary with a total luminosity about 15 times that of the sun. And so Mizar really is a rather complex system. And here we have a representation of it. Mizar A, a spectroscopic binary. Mizar B, also a spectroscopic binary. And a third spectroscopic binary with Alcor. Note that Ludwig's star is not shown there because it's not connected with the Mizar system and is really right in the distance. I don't really think that the stars in the Mizar group are suited to have planets going round them, certainly not inhabited planets. But let's use our imaginations. What would we see if we lived on a planet going round a star in the Mizar system? And I think the scene might be something like that, with 4 bright suns and 2 dimmer ones, and the night sky would be really spectacular. Whether there is anyone there, I don't know. I rather think not. But it's an interesting thought. You know, it's always worthwhile going out and finding the Plough. It is, after all, the most famous of all our northern constellations, and is particularly suitable as a star finder because it never sets over here and you can always see it somewhere. So there we have it, Alcade, Mizar with the companion Alcor, Megrez the fainter one, and the 2 pointers to the pole star, Merak and the orange Diopé. But of all those stars, much the most interesting to my mind is Mizar. And with any small telescope, you will see the group well. There is Mizar itself, down to the lower right, made up of 2 stars, Alcor to the upper left, and Ludwig's star in between, giving the false impression of being a genuine member of the group. Well, as I've said, Mizar is 88 light years away, so we're seeing it as it used to be 88 years ago. If there is anyone living on a planet in that system, they'll be able to see our sun appearing very much fainter than Mizar does to us, of course, because the sun's less luminous. And they'll see the sun as it used to be 88 years ago. And if we really let our imaginations run riot and imagine that there's somebody there with a telescope powerful enough to see our Earth in real detail, well, if he's looking at us now, he won't see Television Center, he won't see you and me, he'll be looking back 88 years in time. And if he's looking in just the right direction, I suppose he could, in theory, see Queen Victoria. Good night.